Hello and welcome. Today is the fifth day of our 8 days problem solving series. We have come up again with another interesting problem. We are given a sequence of positive integers in arithmetic progression with common difference 2. Also, we have given another sequence of positive integers which are in geometric progression with common ratio 2. If a1 is equal to b1 is equal to c, then we need to find the number of all possible values of c for which twice of a1 plus a2 up to an is equal to b1 plus b2 up to bn holds for some positive integer n. In the first sight, this problem might look straightforward, but if we look carefully, it is not so. What challenge do you see in this problem? We will see it as we progress. Let xn and yn be the sum of the terms of ap and gp respectively. By using standard formulas, we can find the values of the sums. We get xn is equal to n square plus nc minus n and yn is equal to c into 2 power n minus 1. We are given the condition twice of xn is equal to yn, which gives c is equal to 2n square minus 2n upon 2 power n minus 2n minus 1. So far everything was routine. Now the challenging part begins. Notice that we have a single equation in two variables. We need to solve this equation for variables c and n. There is no short way to deal an equation having two or more variables. In general, we have infinitely many solutions of some equation having more than one variables. But if the variables are constrained, we may get finitely many solutions. Do we have any constraint on our variables c and n? The answer is yes. Both the variables c and n are positive integers. In fact, there is a fancy term for such equations which are required to solve for integers only. We call them Diophantine equations. But knowing some particular name for some equation doesn't help us in solving it. We are still grappling with the same question. How can we solve this equation? C is a positive integer and we have to find positive integers n in order to make sure that the ratio at the right side turns out to be a positive integer. How can we find such n? Should we simply plug in the values of n starting from 1 and see which one works? Of course, this is not a feasible approach because we cannot try all positive integers n. But wait, do we really need to test all integers? Fortunately, no. If we look carefully, the ratio at the right side, we see that the denominator grows exponentially, while the numerator grows polynomially. It is a well-known fact that the exponential growth is faster than the polynomial growth. In other words, for sufficiently large values of n, the denominator is greater than the numerator. The proof of this fact requires calculus, and it is beyond the scope of this video. Therefore, the denominator is growing faster in comparison to the numerator. So after some particular value of n, say n naught, the ratio at the right side would be less than 1. It means we do not need to manually check for n greater than equal to n naught. And for n less than n naught, we have a hope for c to be a positive integer. Now our job is to find n naught. More precisely, we need to find the minimum value of n naught so that for each n greater than or equal to n naught, the denominator is greater than the numerator. It means we have to solve this inequality. As we expect that for some initial values of n, this inequality would not hold. We manually try the values of n starting from 1. As we notice that for n equals to 1, 2, 3, 4, 5 and 6, the inequality does not hold. After that, as we expected, the denominator is turning out to be greater than the numerator. But we need to give a formal proof that for every n greater than or equal to 7, the inequality holds. We shall give the proof at the end. For now, let's take it granted. Now we have 6 positive integers for which the numerator is greater than the denominator. It means for some or all of these 6 values of n, we might get c, a positive integer. So we simply find c for each of these 6 values of n. And we notice that n equal to 3 is the only value for which we get c, a positive integer. Therefore, there is only one possible value of c for which the given condition holds. Thus, the answer is 1. This completes the solution. Now we give the formal proof of the inequality for which we promised earlier. We present the proof in the form of lemma. We need to prove that 2n square plus 1 is less than 2 power n for all n greater than or equal to 7. We manually check for n equal to 7 the inequality holds. Of course, we shall not check it manually for all n greater than 7. The idea is that if we could show that when we increase n by 1, the increment at LHS is less than the increment at RHS, then it would prove the lemma. We see the increment in both sides when we increase n to n plus 1. The LHS is increased by 4n plus 2, while the RHS is increased by 2 power n. It means proving 4n plus 2 less than 2 power n for all n greater than or equal to 7 is sufficient to prove the lemma. For proving this inequality again, we see the increment at both sides when we replace n by n plus 1. The LHS is increased by 4 and the RHS is increased by 2 power n. It means proving 4 less than 2 power n for all n greater than or equal to 7 is sufficient to prove the last inequality and hence to prove the lemma. It is obvious that 4 is less than 2 power n for all n greater than or equal to 7. This proves the lemma. This was an excellent problem based on comparing exponential growth and polynomial growth. We use the fact that the exponential growth is faster than the polynomial growth to make sure that our manual search for finding positive integer c is not endless. Also, notice that we wanted to solve the equation for positive integers n and c. Instead of directly jumping to find positive integer c, first we narrow down our search for such n which gives c greater than or equal to 1. And then among such values of n, we found those n which give c a positive integer. In other words, first we weakened the constraint to narrow down the values of n, and then we eliminated the undesired values. This strategy of weakening the constraint is commonly used in number theory problems. That's it in this video. Our next problem is based on trigonometric inequality. Make sure you attempt it before watching the solution. Thank you for watching this video. See you next time.